Okay, guys, good afternoon. So, in our last class, we saw a video about the existence of an electron, how to calculate the mass to charge, and how to determine the mass of an electron with different experiments. So finally, before we start seeing the isotopes and how to calculate the atomic mass units and the percentage of isotopes in an isotopic mixture, I want to show you a video about how to determine that experimentally using a spectrometer, mass spectrometer.
Subtopic 2.2, the mass spectrometer. The mass spectrometer is a vital instrument in many kinds of chemical analysis. But how does it work? And how do we interpret the data that we get from it? A mass spectrometer works in 5 stages. First, the sample is vaporized. Then, it is ionized. Third, it is accelerated. Fourth, it is deflected. And fifth, it is detected. The deflection stage is the heart of the mass spectrometer. When we accelerate an ion, it would like to keep moving in a straight line. This tendency of the particle to move in a straight line, its momentum, is proportional to its mass. However, in a mass spectrometer, we use electromagnets to try to deflect the ions off their path. The amount of force that the ion feels from the electromagnet is proportional to its charge. The path that the ion actually takes is a result of its mass-charge ratio. A different particle with a different mass-charge ratio will take a different path. And this is what we are actually detecting, different mass-charge ratios. So let's analyze a sample. We vaporize it and ionize it, accelerate it, deflect it, and then detect it. We can record its mass-charge ratio. If we repeat this with more of the same sample, we will record different size fragments. Eventually, we'll know the proportions of all the different size pieces in our original sample. So how do we interpret mass spectrometer data? Let's consider rubidium for an example. Here's some mass spectrometer data from a natural sample of rubidium. It tells us that 70% of this sample of rubidium was the rubidium-85 isotope, while the rest was the rubidium-87 isotope. If we multiply the percentages times their mass and add that up, then average that over 100 atoms, we'll find the average atomic mass of rubidium. Let's try the reverse. Let's calculate the relative abundances of boron-10 and boron-11 isotopes. First, let's imagine we had 100 of these boron atoms. Let's call the number of boron-10 atoms x. Then, the number of boron-11 atoms has to be 100 minus x. We can put this together to calculate the average atomic mass, which we already know for boron if we look at the periodic table. Do a little algebra, and it tells us that x is equal to 19, which is the percentage of boron-10, and therefore boron-11 has an abundance of 81%. That's it. Thank you for watching.
Well, guys, here you can see how we use mass spectrometry to determine the atomic mass units of elements and the isotopes. Also, we do that to calculate the molecular weight of compounds. So as you can see from basic experiments we saw last time, now we reach to something that we can calculate easily. So let me go now on our stuff. And I wanted you to understand the meaning of that, because we need that to calculate further the percentages of isotopes. We need to understand first what is an isotope. So in modern atomic theory, we know that we have a nucleus, and in that nucleus we have protons and we have neutrons, and we know that surrounding them we have electrons. But basically the mass of electrons is negligible. So we can consider that as 0. So the mass of an atom is coming from protons and neutrons, basically. And so here you can see certain quantities, and here you can see how small is the mass of an electron. So see that? We saw that from before. And now let's see the nomenclature we use for isotopes. So first, let's see what is the meaning of the atomic symbol, the number, and the mass. So in this case, whatever you will see on the periodic table, data coming from the periodic table will be given by the symbol of the atomic element in that case. So you will have a bottom number, and that bottom number, which is C, is the atomic number, and that is the number of protons. And of course, we interpret that as the number of electrons in a neutral atom because we know that for an element to be neutral, the number of protons must be exactly the same as the number of electrons. The top number corresponds to the mass number. And remember, that is coming from the sum of the mass of the nucleus. That contains something that you can measure because the electrons are negligible. So it's the sum of the protons and the neutrons. But what is the meaning of that? Well, the meaning is that you will see on the periodic table, and I'm going to show you that later, is that in many cases, the number of protons, many, not all, in many cases you will find the number of protons is exactly the same as the number of electrons. But this is until a certain number. After that, you will see that the number is different. Yes, so you have more neutrons than protons. Yes? So the number that you will see on the top part of this indicates the sum of the protons and the neutrons. But in many cases, you will find that the number of protons is not exactly the same as the number of neutrons. So it's important to know that you can have similar atomic number in certain cases, but different mass numbers. When that happens, when you have a mass number which is different to the atomic numbers, and you have similar atomic numbers but different molar masses, you are talking about an isotope. So an isotope are atoms of an element with the same number of protons but different number of neutrons in that case. So isotopes have exactly the same atomic number but different mass number. And here you have a case in uranium in this case. So here you can see the number of protons of uranium-235. So in this case we have 92 protons and we know we have 92 electrons. Yes. But the difference in between the top number and the bottom number will give you the number of neutrons. And as you can see, if you multiply these by 2, it's not exactly the same as that. Yes? So that difference is the number of neutrons. And here we have uranium-238 in that case. So here we have an example of two isotopes. In the mass spectra I showed you before in the video, you can determine even the percentage ratio of the two isotopes. And what we have in the periodic table, let me show you the periodic table before we continue here. Why is not? Oh. Yes. So take a look here. What you see on the periodic table, oh, you don't see all the details, but what you see in the periodic table is just the average. Yes? So in this case, what you see is the average. It's the average in between all the isotopes of every of those atoms. This is what you have. So let's see how to solve these type of problems. So first we have silicon, and it has 3 naturally occurring isotopes, which are silicon-28, silicon-29, and silicon-30. Determine the number of protons, neutrons, and electrons in each silicon isotope. So it's really simple in that case. So in this case, we can say that silicon-28 has 14 protons, 14 electrons, and 14 neutrons. This number is coming from 28 minus 14th. And in that case, what we need to is just find here this number from the periodic table, 14th. The second one is 29 minus 14. The third one is 30 minus 14th. So by difference, you can determine how many neutrons you have in that case. So this is really simple. Here, what you can see is how we can form an ion. So we can form an ion in different ways. You can form an anion, and you can form an cation. To form a cation, what you need is a source of high-energy electrons, and you just pull the trigger, and these high-energy electrons collide with the surface of an atom. Suppose that atom is neon 20. So if that energy is enough, that energy will detach one of the electrons from the shell of electrons, the valence shell. So one electron will be detached, and this atom has one less electron. So in this case, you have more protons than electrons, so that's why you pass to neon plus in this case. And as you can see also, you reduce the shell of electrons because you have one electron shell less. So here's the explanation of the mass spectrometer, but I showed you that before. And now let's see how to solve problems of abundance. So I know the video shows you one of that, but let's go over this. So silver has this number of protons. Yes, C is equal to 47, and has two naturally occurring isotopes, silver 107 and silver 109. From the mass spectrometric analysis calculate the atomic mass of silver. So in this case, as you can see, we have different abundances. And we know the value that we will find in the periodic table for silver is coming here, 107.9, is coming from these abundances we have in here. So the problem is really simple to solve. We multiply the atomic mass number of each of the isotopes times the percentage, but in this case, we just divide by 100 to have that based on a 1 number, and we have the atomic mass unit based on the percentage, and here we have the mass portion of silver 109. So finally, we have these two, we sum the two, and finally we have the molar mass that we have on the periodic table. In this case, in the periodic table, you have that rounded, but it's 107.87 is the real number. So now let's go for the real problems, and I want you to do this now in your notebook, please, and we will discuss that in the board later. So in this case, example number 1, there are two stable isotopes of chlorine, chlorine 35, and that is the weight in atomic mass units. And we have chlorine 37, and this is the weight in atomic mass units. If the relative mass of chlorine is 35.45, that relative mass is the mass that you will find on the periodic table. If you pay attention, chlorine is here, and that mass is coming from this number on the periodic table. Yes? So what is the abundance of each isotope? So remember, from the problem you saw before, you can consider that the sum of these two in percentage is 100. But you can also consider that the sum of the two is 1. Yeah, you can consider 1 as 100. So then after, you can find the proportions of each one of them, finding x and finding y. So you need to establish a simple two-system equation for this case. Just try to do it, and then after, I will show you that on the board. So we have these two. We have chlorine 35, and we have chlorine 37. So let's put them together, and let's consider this chlorine as X and this chlorine as Y in our system equation. So we know for the first system equation is that X plus Y is equal to, well, you can make them equal to 1 or you can make them equal to 100. It's up to you. You can decide that. I use 1 because it's easier. Okay? So if we make them, the sum of the two will give you 1 or 100. Because we know that 100 is composed by just the two. But then after, we need to transform the sum of these two based on the ratios into the value that we find in the periodic table. So we can establish a second system equation for this case. And that second system equation will be X times the atomic mass unit for X is 34.97 plus Y times the atomic mass unit 36.97 atomic mass unit, and that value is exactly the same as one we have on the periodic table, which is given, by the way, in the problem. So in this case, that value is 35.45. I will continue on this board. So here, we know from the first equation that X will be equal to 1 minus Y. Yes? So now we can use this on the second equation and have only one variable. In this case, we can have only that value, which is, in this case, X or Y. So the idea is that we substitute X by 1 minus Y, so it will be 34.97 times 1 minus Y plus 36.97 Y is equal to 35.45. And if we continue going here, we have 34.97 minus 34.97 Y plus 36.97 Y is equal to 35.45. Then, well, you can keep going. Now you solve Y. And once you solve Y, it's easier to solve X. Just multiply those numbers by 100, and you will have the percentage abundance of each one of them. So really simple to solve it. Okay? So you construct a simple two-system equation like that, and then after it's easy to get the answer in that. Solve that, and you will have the answer. Of course, you need to multiply Y's and X times 100, you will have a percentage, okay? Now let's do the second exercise. The second exercise, as you can see, is exactly the same. Well, not exactly the same. It's very similar to the previous one. But let's read that carefully. So in this case, there are two naturally occurring isotopes of lithium. Lithium-6, and it has that atomic mass unit, and lithium-7, it has that atomic mass unit. What is the abundance of each? So as you can see, it looks the same type of problem we saw before. But what is the difference? The problem is not giving us the relative atomic mass unit that you will find on the periodic table. So if the problem is not giving you that, you can extract that from the periodic table. So we need to look at the periodic table for lithium, and here is 6.941 atomic mass unit. So what you need to is, in this case, construct again the two-system equation. Okay? And x plus y is equal 1, and then you multiply x by the atomic mass unit of one isotope plus y times the atomic mass unit for the second isotope, and that number is equal to 6.41. After you solve that, you will solve the two values, multiply them by 100, and you will have the answer in that case. Any question till now? No? Okay. Now let's see the details of the periodic table. In the periodic table, we have 4 different important parts. I will consider even like a 5th one. So the first is this block. And in this block, we contain the alkali metals of groups number 1 and 2, where we have lithium, sodium, potassium. We have beryllium, magnesium, calcium, strontium, barium, and so far. So this group is the alkali metals on the left. There is one exception, of course. And we know that hydrogen is not a metal. The top column you have on the right is composed by the noble gases. The noble gases, helium, neon, argon, krypton, xenon, radon, and so far, they have a very important characteristic. They are so stable. And all of the remaining elements of the periodic table will try to react to get the stability of the noble gases. So the idea of the reaction of the remaining elements is to get the same stability, or at least partially similar to the noble gases. And we will see that all of them try to get the octet rule, at least the same type of configuration that they have in the periodic table, the noble gases. Of course, the octet rule just applies for elements on the second row, not below the second row. Then we have this group here in this block, this light blue block, which is composed by the transition elements. All the transition elements are metals also, but they have certain different characteristics than those from the alkali metals from groups 1 and 2. We have the inner transition metals in this case. Most of them are unstable, most of them, not all, but most of them. And finally, we have this green group here, which is in the interface of the metals and the non-metals, and these are called metalloids. In this case, we have boron, silicon, germanium, arsenicum, and so far, antimony, and so far. So all of them have different properties. And, well, I won't discuss with you all the properties, but, for example, the metals, they shine. All of them are solids. In the case of the non-metals, they can be like this on the metalloids, or these are metalloids, not non-metals. And in the non-metals, you can go from the solid state to the liquid state. In the case of iodine, for example, iodine is solid, bromine is liquid, and chlorine is a gas. So you can go from solid to gas to liquid and to solid again. So how to form an ionic compound? First, we need to recognize what is an ionic compound. An ionic compound is composed by 2 parts, a cation and an anion. The cation has a positive charge, and the anion has a negative charge. So we saw before how to form a cation. We just detach one of the electrons from the valence shell, and we can form a plus in that case. But also, you can see here that in the ionic compound, you have the 2 parts, the anion and the cation, and they are attracted in between by electrostatic forces. and they form what we call commonly salts. The most important thing you need to remember till now from these type of compounds is that the attraction depends on two things. This attraction in between the cations and the anions depends, one, in the size of both the anion and the cation, and second, on the distance that separates the both. So when you have a big size in between them, okay, the forces of attraction are less because the distance of separation in between the two is less. And when you increase the charges, also the forces of attraction becomes higher. But we will see that later in the forming of ionic bonds. Now let's understand how these ions are formed, and then after how they form these ionic compounds. So let's interpret again the periodic table meaning. So I told you before that on the right side we have the noble gases, which are pretty stable. So all the remaining elements will try to do a couple of things. Some of them will try to release electrons to form cations and acquire the same configuration of the previous noble gas. That is an example of sodium cation. For example, you have sodium here, and sodium forms cations very easy. And the reason is that sodium releases one electron, and it acquires the same electronic configuration of neon, which is the previous noble gas. So for the left side elements, methyls and alkali methyls, it's really easy for them to release electrons and form cations because they acquire the same configuration of the previous noble gas, which is stable. But on the right, we have the non-methyls. So on the non-methyls, suppose you have the halogens here. The halogens, for them, is easier to acquire one electron instead of release one electron and get the configuration of the next noble gas. So the case of fluorine, for example, is easier for fluorine to get one more electron and acquire the configuration of the next noble gas, which is neon. So the reason why some element forms cations and anions is the easy they can form or they can be transformed in the electronic configuration of the previous noble gas in the case of the methyls or the next noble gas in the case of the non-methyls in that case. So depending on how far they are from the noble methyl, they will acquire 1, 2, 3 electrons, or they will release 1, 2, or 3 electrons. So let's consider the elements from the group number 1. Here, in this case, lithium, sodium, potassium, and so far. So if they lose one electron, they will acquire the configuration of that, and the charge of them will be +1. In the case of the second group, 2A, beryllium, magnesium, calcium, strontium, and so far, the charge is +2 because it's easier for them to release 2 electrons and acquire the configuration of the previous noble gas. That's why they have charge +2. But in the case of the halogens like fluorine, chlorine, bromine, iodine, and so far, so in this case, it's easier for them to get just one electron and become the next noble gas. In the case of the oxygen, sulfur, and so far, oxygen and sulfur has a -2 charge because it needs to acquire 2 electrons. And in the case of nitrogen, it's 3, and so far. So this is the interpretation of the charges we see for these ions. Okay, how far they are from the noble gases and how easy it is for them to lose electrons, release electrons, or to gain electrons. So that's why you can see here the group. Here you have on the center the noble gases, and here you have 1A, 2A, and 3A. You have +1, +2, and +3, 7A, 6A, and 5A, -1, -2, and -3. So in this case, it's easy to predict the monoatomic ion forms for each of the following elements: iodine, calcium, and aluminum. So if we go back, it's so easy. Iodine will have -1, it's just close in this case to xenon in the periodic table. Aluminum is +3, it belongs to the group 3A. So it's easy for it to release 1, 2, and 3 electrons and get the configuration of neon. And in the case of calcium, is +2 because calcium belongs to the group 2A, and if you check here, calcium is here, release 1 and 2 electrons and get the configuration of the previous noble gas, in this case argon. So those charges are coming from that. Now let's see what happened with the covalent compounds. What happened with molecules that have covalent compounds. So in this case, you have a covalent compound when you have two elements sharing electrons. So in the ionic compounds, we have one atom or one group is donating electrons and the other one is just receiving those electrons. So one becomes positive and the other one is negative. That happens in atoms that have a property we'll see later called electronegativity. And electronegativity is just a capacity of an atom to attract electrons. Yes? So atoms in the periodic table, they have different electronegativity. For example, the most electronegative atom of the periodic table is fluorine. Yeah? When you have two atoms with a high difference of electronegativity, those will form a ionic compound. But you have elements which are the same or are having a small difference of electronegativity, like, for example, two non-metals together, or two atoms of oxygen, or two atoms of hydrogen. There is no difference of electronegativity, or really small difference of electronegativity. So instead of forming an ionic compound, they will share those electrons. I give you one electron, I receive one electron, we share together, and in that case, we form what we call a covalent compound, or a covalent bond. So here we have the example of hydrogen, one proton, one electron, one proton, one electron. They just share one electron, and they form, finally, the hydrogen molecule, because hydrogen atomic number is 1. So now, we can do a top hat question, please, before we leave. Very easy one. We will do 2. Just be prepared for them. These 2 questions are really, really easy. And it's because it's your first trial. I want you to be familiarized with them, okay? Not all of them will be that easy. Remember, 0.8 points is just participation, and 0.8 will be the correctness in every case. You ready? Okay, start with the first one. Read carefully. If you need more time, I can give you some seconds more. How many electrons belong to a neutral atom with an atomic mass of 39 atomic mass units? Forget about the periodic table. Do not search anything on the periodic table. Just interpret that. Again, do not see the periodic table. Just interpret that. Suppose you don't have a periodic table. How many electrons belong to a neutral atom with an atomic mass of 39? You have 4 choices. Yes? You can discuss in between if you want to. You are free to. I will give you 15 more seconds, okay? Try to be quick. Guys, hurry up. $15 more. Last 15, promise. Huh? Wait. Okay, guys, this is all. What was the correct answer? It was D. Yes, why? 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 The problem is giving us atomic mass number. And the atomic mass number will come out from what? The sum of what? Protons and neutrons. Yes? Yeah? Do you have any idea on how to calculate the electrons if you don't have the protons? And you know that in many cases, the sum of both won't give you exactly the same numbers. Yes, in the case of protons and neutrons. So you cannot determine that using that data. Okay? Easy. Let's go for the next one. Really easy. And in this case, you need to see the periodic table. Really easy, it's a gift. Which second row element prefers to form a -2 anion? Enter the element symbol only. You need to type the symbol, okay? You need to type the symbol. Guys, what was the symbol? Oxygen. Yeah, so simple, yeah? Second row, and it needs 1 and 2 electrons to get the neon configuration. Yes? Only 2. Yes, -2. Really simple. Okay, guys. Let's continue and finish the class in the next 9 minutes. So let's go back on the terms molecules and ions. In the case of molecules, we have the molecules are the basic units of an element or covalent compound. Yes, it's a covalent, consisting of 2 or more atoms bonded by sharing of electrons. So in a molecule, you have only covalent bonds. That is a huge difference. So you can have compounds which are molecules, that's true. You can have also compounds which are not molecules, and those are the ionic compounds. And the ionic compounds are composed by 2 ions, a cation and an anion in this case. So the ions are single atom or covalently bonded group of atoms that has the overall electrical charge. They are not molecules in an ionic compound, but be careful. In an ion, you can have covalent bonds or not. It depends on what type of ions are you talking about. So you can have a single ion like this. You have an anion, or you can have potassium cation like that. But also remember, you have you can have also polyatomic cations and anions, and I will give you a couple of examples. So in this case, we have ammonium ion. And in that ammonium ion, you have a structure, and we will discuss this later in the class. Not today, of course. You have this, and what you see there is you see 4 covalent bonds. So you have a cation, but that cation, not the entire compound, has covalent bonds inside. So the same happens with anions like this. Carbonate. In the case of carbonate, the structure, and we will see this with resonance later, and in Lewis structure, has this structure here. The dots represent electrons, and I will explain that to you, not for this exam. So as you can see here, we have a polyatomic anion, and inside that polyatomic anion, you have covalent bonds. But, for example, sodium carbonate or potassium carbonate is not a molecule. Yes, it's an ionic compound. Be careful about that. Also, we have polyatomic elements. No, we don't have polyatomic elements. What we have is molecular elements. Yes? So in molecular elements, you have elements on the periodic table that cannot exist alone. So most of the elements do that, with the exception of this, what you have in there. Okay? So these are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, sulfur, phosphorus, and selenium. These are the only cases, so you need to memorize this. Please don't forget that. The remaining ones exist as monoatomic. Here, I'm just showing you the structure of carbonate, but I draw that on the board before, so I won't go over that. Now let's interpret the chemical formulas. The chemical formula consists of lettering symbols and numerical subscripts. And that is indicating us the smaller whole numbers that can be together bound to find a chemical compound. Yes? So the chemical formula tells us the type and number of each atom present and the smallest units of the substance. So let's see the naming. Finally, nomenclature. And the naming is based on IUPAC. IUPAC is International Union of Pure and Applied Chemistry. So let's go for the simple ones. Binary. Binary ionic compounds. So ionic compounds are composed by a cation and an anion. So in this case, we are not talking about polyatomic cations or anions, just simple ones. So in this case, the name of the cation is the same as the name of the methyl and goes first, from the left to the right. And many methyls names ends on ion, but not all of them, and I will show you the examples. And the anion is named by adding the suffix "I" to the root of the non-methyl and goes second on the right. So for example, calcium and bromide forms calcium bromide. So here you have a table, and you need to memorize this, okay? So, however, there is a way on how to give you certain guidance, not if you fail on the memorization process. Okay, so here you have the ones having charge +1, +2, +3, and you have the anions having -1, -2, and -3. So these are relatively very simple, and you can determine those numbers just seeing the periodic table. Yes? So here you can see in the alkali methyls that number +1 comes from the group number 1. Yes, so group number 1 will have on the left +1, lithium, sodium, potassium, rubidium, cesium, francium. Group number 2 will give you +2, magnesium +2, calcium +2, strontium, barium +2. And in the other side you have group number 7 in this case, and that number 7, well, will give you, in this case, not the number 7 will give you the charge, just the separation from the right in that case. So -1 from group number 7, -2 for group number 6, -3 for group number 5. It's easy to just use the periodic table, and remember that the problem arises with the transition metals, this block here. Because in the transition metals, you can have metals with different charges possibilities or different valence values. So the only way is just to memorize them. And that's why you need to in those cases. So here you can see what happened with the transition metals. So in this case, chromium can work with +2 and +3, iron +2, +3, cobalt +2, +3, copper +1, +2, and so far. So the problem are the transition metals, basically. So to name those compounds and give the molecular formulas, what you need to is just exchange the charges, okay, from the tables and use the subindexes in this case. You don't need to place 1 as a subindex. Something which is bigger than 1, you need to. For example, in this case, we have magnesium and nitrogen. We know that magnesium is here. Magnesium is here, is +2. And in this case, we have nitrogen. Nitrogen is -3. Yes? So magnesium, okay, and the nitrogen. You exchange those numbers, and you will have Mg3 and 2. And that is the molecular formula for magnesium nitride. Iodine and cadmium, sulfur and cesium, and so far. So this is the exercise you need to do just using the previous tables. So for the first, magnesium nitride. For the second, cadmium iodide. For the third, strontium fluoride. And for the last one, cesium sulfide. So I will stop here. And next class, guys, I will start with the calculations. Every calculations we need to do next class, okay? Guys, try to study all the names for the cations and anions for next class. So we can go faster if you remember that, okay?